Hello and welcome to Calculus tutorial. We are going to take a look at the second fundamental theorem of calculus now. So if you remember before, when we did the first fundamental theorem of calculus, that connected the ideas of the indefinite integral and the definite integral. The second fundamental theorem of calculus connects the integral with the derivative. And this just basically mathematically says something that we have been sort of assuming since the beginning of the semester, that the antiderivative, the integral, is the opposite of the derivative, and opposites undo each other. So here is a formal way of stating the second fundamental theorem of calculus. If you take the derivative of an integral, they cancel each other out, and you're basically just left with f is equal to f, which we've sort of assumed all along, that the derivative and the antiderivative were opposites of each other. But this just states it mathematically. Now there's some other things in here that I'm guessing look a little weird. Like this is the definite integral from a to x, we've never seen that before, of f at t dt is then equal to good old f of x. And so I'm guessing this right here looks a little weird. Why does that have to look the way it does? I'm going to try to explain that to you, but all in all, just remember that this is just saying the derivative and the antiderivative cancel each other out. So let's take a look at that definite integral and try to figure out what does that mean. And so I'm first going to simplify it. Instead of having an a down here, I'm going to put a 0 to give us a definite starting point. So what does the integral from 0 to x of f at t dt mean? Well, that is going to be a fancy way for us to make a definite integral into an indefinite integral. If I take the indefinite integral of cosine, the antiderivative of cosine is just sine. And so if I take the integral from 0 to x, and so that's going to be this area right here that you see, I'm going to take that area and plot it as a point. So here the area is 1, and so this point is up here at 1. And as it keeps going, now because the area is negative, that number is getting smaller. And take a look at the path that takes. If it's a little hard to see, I can make it trace. As you can see, fill in all the gaps here. That makes a sine curve. Here, I'll trace it for us. It's harder to do than you might think. Alright, so there is our sine curve right there. And if I take the derivative of that sine curve, it will get me back to cosine. Well, now that works when this is 0. What happens if that is not 0? Well, I can change that. So let's try like a -2. What if it's a different number? Alright, so that changed my area down here, see? It's different. It also changed where the point was. Is that going to be a big issue? Well, let's follow the path of this point again. As you can see, it's still a sine curve. Is it the same sine curve? Well, no. So the integral is different. But as you can see, they are parallel. Parallel means they have the same slope. Another word for slope is derivative. So they have the same derivative. So when I add the derivative here in front, just because it's moved up does not affect the slope. The slope will still be, oops, sorry about that, it's the wrong thing. It does make a sine curve, but when you take the derivative of that sine curve, it brings us back to cosine. Because the derivative of sine is cosine. So that weird integral there with an x on top is just a fancy way to turn this into a function. and it makes a curve, it turns the definite integral into an indefinite integral. All right, so again, in summary there, where am I here? The derivative and the integral simply cancel each other out. Okay, so let's take a look at some examples there. How does the second fundamental theorem of calculus actually work? Let's start with some easy ones. If the graphic view didn't make it understandable to you, maybe the algebraic work will. So first, let's take the antiderivative here, and then we'll take the derivative. So this is just going to stay here. We're not going to think about that. Let's take the integral. So here we're going to get 1/3 t cubed minus 5t will become 5/2 t squared plus t, and we're going to evaluate that from -2 to x. Got my parentheses a little off there. Okay. So the derivative is still there, remember. Let's actually plug these in. Well, if I plug in x, the t's are just going to become x's. So 1/3 x cubed minus 5/2 x squared plus x minus. Now let's shorten this a little bit so I don't have to do all the math in my head. Are you with me that if I plug in -2, boom, 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 that we are going to get a number? Okay. Let's call it 25. Is it going to be 25? No. But for the purpose of this, you'll see that it doesn't matter. I know it's not going to be 25. Because all I'm going to do is take the derivative now. So the derivative of 1/3 x cubed, 3 multiplies down, you get x squared. Take the derivative of this one, 2 multiplies down, you're left with 5x. The derivative of x is 1, and the derivative of this number, which we know is not 25, is still 0. And so this is what we get. Now take a look at what we started with. The derivative and the antiderivative canceled each other out, and all of our t's became x's to bring us to here. And that will always happen. So in the end, hopefully you saw that the -2 didn't matter, because when you take the derivative of a constant is 0. So let's do this one the short way. I know the 3 doesn't matter. I know when I take the integral, it's going to be canceled out and undone by the derivative. So the x is simply going to be plugged in where the t's are. So we are going to get 5x squared times e to the 2x as our derivative there. Nice and easy application of the second fundamental theorem of calculus. It's a good thing that worked out so easy, because you could not do that antiderivative the way it is. Not by hand, at least. All right, so there's 2 easy examples of how you can do that. This is sort of the proof, because we worked out all the steps, but you actually don't have to work out the steps, because we know the x will just go in for the t's. All right. Sadly, it doesn't quite end there. It gets a little bit more difficult because I can throw a curveball at you where you have to use or think about the chain rule. So let's take a look at that. And so hopefully you'll see the main difference here is that the top number is no longer a plain old x. It is an x squared. That makes things a little more difficult for us. So let's do this the long way to see what happens. So we're going to save the derivative for the end. let's take this antiderivative. So that will be 5/2 t squared minus 8t evaluated from 1 to x squared. So when we plug in x squared, here's where this gets a little weird. The 5/2 is there still. But if I plug in x squared in for t, we will have x squared squared minus 8, and this one's easier, x squared. Minus, if we plug in 1, we will get a number, but we really don't care what that number is, remember? Because we're going to take the derivative, and the derivative of whatever that number is will be 0. Alright, so we're going to take the derivative with respect to x. This will become 5/2 x to the 4th minus 8x squared minus a number, which is going to be equal to 4 multiplies down, cancels out the 2, but there's still 2 left over, so we will get 10x to the 3rd minus 16x. That's a problem, isn't it? We do not get simply this turning into an x. So what's the easy way to go from here to here? Well, it's not obvious the way we have this written, but it would be a little bit more obvious if we factored this. So factor out, let's see, we can factor out a 2x times what's left over here, 5x squared minus 8, it looks like. Okay, now we're getting somewhere. Doesn't this kind of look like this? So what you do is the x squared does go in for the t. So you get 5x squared minus 8. But you don't just stop there. Because you're taking a derivative and now you have a function inside, hopefully that sort of points towards the chain rule, we have to multiply by the derivative of x squared. What's the derivative of x squared? 2x. And now we've got exactly what we have over there. So yes, that still goes in for t, but if you have a weird function up here, you have to multiply by its derivative. The derivative of the outside times the derivative of the inside kind of thing. So what does that mean for one over here where we can just use the shortcut? Well, this will go in for t. So we'll have cosine of 4x squared. But then we're going to have to multiply by the derivative of the inside, which is this, which will be 8x, it looks like. And if you want to put the 8x in front, it makes it look a little nicer, I suppose. Although not when you have bad handwriting like that. It's all good. Oh, that was a terrible parenthesis. There we go. All right, so there we have it. If you want to check that one the long way, you can, but I won't do that. All right, so that is the second fundamental theorem of calculus. Just got to be careful when that top number is not a plain old x. You have to remember to multiply by its derivative. All right, so that is the second fundamental theorem of calculus. It takes the integral and the derivative and relates them to each other. In short, it proves that they are opposites, that they undo each other.